Okay, good afternoon. This is our lecture number 29. In the previous lecture, we have been discussing about the measurement of void fraction, and then we also tried to see that if we measure the value of phase density function at a different finite number of points at any cross section, then even we can actually reconstruct the interface and we can see that how phases are distributed. Okay. After that, we will now try to see different methods for measurement of velocity, because velocity is also an important parameter which we should be able to quantify experimentally. Okay. So typically velocity measurements, if I simply talk about velocity measurement, then can you tell me how or what type of measurement we want to do? So let's not answer how first. When I name the term velocity measurement, what do you understand? What type of measurement we want to do?
Time varying distance measurement.
Time varying distance measurement. Okay, so typically if you see in a fluid medium, there can be measurement of two types of velocities. Okay, one velocity is average velocity of the mean flow at any cross section, and second velocity measurement can be localized velocity measurement at each and every time, at each and every spatial location of the cross section. Okay, so typically if you see, for example, when we consider the flow through a pipe, so in laminar flow through a pipe, we say that if we move away from the, particularly under the Poiseuille flow conditions, if we move away from the center, then value of velocity decreases and at center it is highest. So it means my velocity profile will be something like this. So whenever I am talking about this type of velocity profile, it means that at the cross section I am measuring velocity at different locations in the y direction, if this is my y direction. Is this point clear? So this type of velocity measurement is nothing but local velocity measurement. On contrary, if my only interest is to determine that how much amount of average velocity is actually going through this pipe, okay, so particularly the fluid which is flowing through this pipe, what average velocity it is having. So then we need not to go for that much localized measurement. We can use some more known methods which you have actually already studied in your undergraduate courses, such as venturimeter, orifice meter, etc. Okay, so in case of obstruction based meters, so venturimeter, orifice meter, all these are nothing but the obstruction based flow meters. So in obstruction based flow meters, we employ the change in pressure at two different locations to measure the average velocity. Okay, so that is how actually we can determine the value of the average velocity. But whenever we will be talking about over here the velocity, we are actually interested in determining the local value of the velocity at each and every spatial resolution. Okay, because if you have to measure average velocity, then you already know the standard methods. Okay, so that is our interest. So typically the measurement of local velocities for single phase flow is difficult in comparison to the measurement of the velocity for for multi-phase flow is difficult in comparison to single phase flow, because in case of multi-phase flow you will be finding that there are multiple phases and all the phases are not moving at the same velocity. So all the phases are actually, so whatever number of phases you may have, there will be actually always relative motion between them. Though one of the assumption we make that we are having homogeneous flow, so under the homogeneous flow we say that the velocity of both the phases is same, but that is also a very idealistic situation. In real circumstances you will be always finding some difference of relative velocity between the two phases. Okay, then majority of the time our interest in velocity measurement is of some peculiar structure. That structure can be a gas bubble or liquid slug. Okay, so when I am talking about the multi-phase flow, of course majority of the time our interest may be to determine the velocity of the continuous phase, but many time our interest may be to determine the velocity of the bubble which is actually flowing in the continuous phase. Okay, then Okay, so if any of you have idea about the localized velocity measurement, even for single phase flow applications, then you might have heard of the terms such as laser Doppler velocimetry, hot wire or hot film anemometry, or particle image velocimetry. So these are the advanced methods which can be utilized to measure the velocity of at different spatial locations within a fluid medium. Okay, so whenever we will be talking about the measurements of velocity measurements in multi-phase flows, we will be majorly talking about hot wire anemometry and particle image velocimetry, because laser Doppler velocimetry is having very less accuracy in case of the multi-phase flow applications. So typically you know that what happens in laser Doppler velocimetry, this is based on the Doppler's effect. Okay, so whenever you send some signal, there is some phase shift in the signal depending upon the flow situation. Okay, so in case of multi-phase flow, what happens actually, the phase shift is not only because of the flow, but it is also because of the presence of the interface. So presence of the interface many times leads to very weak signal in case of laser Doppler velocimetry, and you cannot differentiate properly in between the noise and the actual signal whatever you are getting from the flow. So that's why for multi-phase flow applications, this method of velocity measurement is not promising. Okay, then other than these methods, so why I am naming these methods, because these are the standard methods which somehow, even if you are talking about the single phase flow, then also you might have heard of. But other than these methods, certain alternative methods are also there which can be utilized for measurement of velocities in multi-phase flow. So one of the method is cross correlation technique, and even then many digital image processing techniques are also developing nowadays which can be utilized for measurement of velocities of the multi-phase flows, but cross correlation technique is something which is having a long history, so it has been utilized by researchers even in the long back 1960s or 70s as well. So LDV measurement, it measures the frequency shift of a laser beam which is scattered by moving object. So that is the basically Doppler's effect, which is principle of this measurement. But as I told you that in case of multi-phase flows, this method is not very much suitable, because when there will be scattering of the beam, it will not be only because of the flow, but it will be because of the presence of multiple interfaces present in the system. So which will be actually reducing the strength of the signal. That is something which I told you. So typically laser beam is also scattered by interfaces and efficiency of LDV is reduced. So that's why its applications were very limited to dispersed flow with low concentration of spherical bubble, when concentration is actually low, because if concentration is low, then the laser beam will be faced by less number of interfaces and signal strength will not be decreasing much. So that's why it cannot be used for very generalized multi-phase flow situations where you are having huge amount of void fraction. Okay. Okay, so before calculating the velocity, let me give you some idea about measurement of mathematical formulation of local velocity. So here you can see this small ukx. So x is nothing but your position vector, and small uk is the value of velocity in kth direction. And typically whenever we are doing the measurement of velocity, we consider that where our mean flow is flowing, our measurement of velocity will be dominated in the mean flow direction. So I can say that, say uk is velocity in the direction of the mean flow, but this uk is nothing but a local time averaged velocity. So now you have two quantities. One quantity will be because of changes in velocity with the space, and other will be changes in the velocity with time. Okay, so let's assume at the moment that either we have steady flow situation where velocity is not changing with time, or we have a significant amount of time interval which we are using for measurement of this local velocity, and this we are considering the local time averaged velocity. Is this point clear? And how to do time averaging, that already I have shown you while I was explaining to you the concept of void fraction using the phase density, phase distribution function. Okay, so this is my local velocity, and if you have to understand this local velocity measurement, the very simple tool is, which you have used even in your fluid mechanics experiments during the undergraduate courses, is pitot tube. Okay, so all of you have used the pitot tube. So typically when you do the experiment of pitot tube in your laboratory, what you do? First you fix the pitot tube at the center of the pipe. Then you measure the corresponding velocity. Then you slightly shift the pitot tube towards the wall. Then you measure. Then again you shift. Then you measure. So it means when you are shifting the location of the pitot tube, you are shifting your measurement probe. Okay, and the point at which measurement probe is located, at that point you are actually measuring your velocity. Though in case of pitot tube it is not precisely the same point, it is slightly upstream of that point, because in case of pitot tube what happens, typically at the probe location your flow becomes complete stationary. Okay, so there the local velocity is 0, but just slightly before that, when the flow was happening and then it was coming to 0, so it gives the value of local velocity of that particular point. Okay, so that is something. Whenever you will be using hot wire anemometer or you will be using particle image velocimetry, anything, when I am referring to the local velocity, it means I am referring to some particular position vector x. Okay, so say, as I told you, that in case of pitot tube, when I am at the center point, then say my position vector is x1. When I have shifted somewhere here, then my position vector is x2. So likewise, if I have to specify the local velocity, I must specify its position vector as argument. Okay, so that's why uk is given as function of x. Okay, so when we do the pitot tube experiment, if I am able to take sufficient number of data points along this point, then I can do averaging of that to calculate the average velocity that at that cross section. So that is something which is shown over here. So if I have the continuous measurement at all the spatial locations, it means at each and every point I am able to measure the velocity. Okay, so if I know the value of local time averaged velocity at each and every time, then I can integrate it over the area, cross sectional area, and then if I divide with cross sectional area, that will be giving my mean flow velocity. Is this point clear? So how local velocity and mean flow velocity are interrelated, that is something which is shown over here. Okay. Now we know that, I will not repeat this. So in case of multi-phase flows, we will be having actually this J, superficial velocity or volumetric flux, which will be Jg plus JL. Then of course we will be having actually drift velocities also. So when I am referring to the small symbols, these are referring to local points, and when I am referring to the capital symbols, these are referring to the overall cross section averaged quantities, mean quantities. Okay, so then another important parameter comes in multi-phase flows, which is called as velocity ratio or slip ratio. So how slip ratio is associated with void fraction, that is shown over here. So this is associated with volumetric flow rates and void fraction. So it means that if you know the slip ratio, then also you can measure the void fraction, or if you know the void fraction, you can measure the slip ratio, etc. Okay, then again slip ratio is presented in terms of the mass flow rates and corresponding mass quality and void fraction. Okay, so that is something, all these relations we have studied earlier, but the major idea over here to again emphasize to you is that if you are able to calculate the velocity of one of the phase, and you are able to, and if you know that what are the flow rates in the pipe you have and what is the void fraction, then you can calculate the velocity of the other phase. Because majority of times this happens that when you are using a probe, you cannot move probe at each and every location. So with the probe you can say get idea of your velocity of the continuous phase, because measurement of velocity of continuous phase is quite easy and measurement of the velocity of the dispersed phase is actually challenging. So that's why many times you can simply measure the velocity of the continuous phase, then you can, if you have idea of void fraction and volumetric flow rates, then you can calculate the corresponding velocity of the dispersed phase. Okay, now comes the very first technique, which is called as cross correlation. Okay, so what do you mean by cross correlation? Any one of you have some idea? What do you mean by cross correlation?
Correlation between two different lines.
Yes, so typically cross correlation is nothing but the correlation in between two different signals. Say I have some signal S1, and if I plot this signal S1 with time, so say this is my value of the signal S1. Okay, then I have another signal S2, and if I plot its value with time, this value is also having the similar variation. Okay, now if I do S1t into S2t, what I will get? S1t into S2t, I will get some larger peak at this point. Okay, I will get some larger peak and then this type of thing. So it means that if I have two signals S1t and S2t, okay, so both the signals are taken at different times. If we multiply these two signals and the nature of the signals is same, if we say that these signals are of similar nature, then if we multiply them and take the sum of their products, then ultimately what we will be getting. So this is only multiplication. After multiplication, if I even take the sum of their products, then what I will get? I will get some large positive value. Is this point clear? But if signals are not self-similar, if signals are not similar, in that case what will be happening? Say one signal is positive, other is negative. Then I may have any value depending upon the nature of the signal. Say at some point it may be positive, some point it may be negative. So some of the products S1t into S2t, some products will be negative and some products will be positive. I will be having mixed nature of the products. Once I have mixed nature of the products, if I do their total entire sum, that will be coming a small quantity. Okay. So there can be two indications to judge whether signals are similar or not. First indication is if we multiply two signals, then all their multiplied products are positive. Okay, even if both the signals having negative nature, then also product will become positive. So if all the multiplied products at each and every time instant are positive, and if we take the sum of all the products, if that is becoming a large positive value, it means signals are self-similar. Okay, if these values are small, then signals are not self-similar. But here, these two signals are actually in the same phase. In many cases, it happens that signals are self-similar, but there is some phase difference between the two signals. Say, one is having peak at this point and other is having peak at some other time. Okay, so now you can see that, let's assume that in between these 2 points you have tau star as the time difference. Okay, so that is the phase difference. Now let's do one thing. I will multiply signals S1t and S2t plus tau. But what is the exact value of tau? That I have not yet decided. Okay, so what I will do now, I will choose different values of tau to multiply this signal. So when my tau is very small, approaching to 0, corresponding to that I will get that this entire product, say this entire product is P. So this P will be coming 0. Okay, once my value of tau is very small. Now if I keep on increasing the value of tau, once I keep on increasing the value of tau, my value of signal will slightly keep on increasing, and ultimately if I consider tau equal to tau star, then I will be getting the highest value of the peak. Is this point clear? All are clear with this?
So in first condition, if tau is equal to 0, then it should be maximum.
No.
It will be as
Let's consider this value is 0, this value is some s. Okay, again here this is 0, this is some s. So when I am simply multiplying s1t and s2t plus tau, so I have taken some value of tau, so it means s1t, say t is my this time instant, so I am multiplying this capital S, but for s2 I have to use t plus tau, and say tau is small, so tau is pointing out somewhere here, so this will become then 0. For this entire section up to this point, this product will be coming equal to 0. Is this one clear? Now you are clear with this idea or not? Not yet. See,
सर ये वाली कंडीशन से पहले जो कंडीशन है उसके सिमिलर ही है तो उस कंडीशन में मैग्नीट्यूड बदल
no, it is similar, but they are both who are actually in the same phase. Okay, there was no time difference between the two. So if at t you are getting s, here also you are getting s, but now at any arbitrary time t, if in signal 1 you are getting s, in second signal at some time t plus tau you are getting 0. Point is clear? Okay, so signals are having some phase. Okay, so it means that if you measure two signals and these two signals are having some time phase, okay, then if you arbitrarily try the values of different phase time phases, the point at which you will be getting highest value of multiplication of the products of signals, that particular time will be corresponding to our that will be resembling the actual phase difference between the two signals. Okay, is this point clear? Now how this cross correlation data can be utilized for measurement of velocity? So what you can do is, say you have a pipe, in this pipe you have a bubble, you will be giving one optical signal from here, you have some detector over here, then again a signal and then detector here. Okay, so what will be happening? Say at some time t1 bubble is at this point, so you will be getting the value of signal something like this. At t1 time value will be decreasing and then again it will be increasing because of the reflection from the interface. So say this is at t1, but when the same bubble will reach to other location, then what will be happening? So this is S1, this is S2. When same bubble will reach to other location, then what will be happening? This signal will be coming showing self-similar behavior at some time t2. Okay. Now, if you are able to determine this difference of t2 minus t1 such that your signal is mathematically similar or mathematically cross correlated, then you can say that that is the time which is taken by bubble to move from this location to this location. And whenever we are mounting these sensors, of course we will be mounting with the known distance between them. Okay, so we will be knowing the distance between them, say the distance between them is d. Now these arbitrary signals we have mathematically made cross correlated, and using the cross correlation function we determined T2 minus T1 such that their correlation is highest. Okay, so corresponding to that highest correlation we can say that these signals are correlated, means corresponding to that time difference the bubble has moved from this point to this point. And now by knowing the difference, by knowing the distance and the time from cross correlation, actually we can calculate the value of the velocity. Okay, this seems very easy at the moment. Okay, but whenever you will be employing it practically, there are many challenges with that. So that also let's try to discuss that what are the challenges with this. So that is what I tried to explain you, that say my signal is such that S1 is equal to S2 into T plus tau star. So tau star is the phase which is showing the self similar behavior of the signal. Then what I can do, I can define some cross correlation function from R1 to 2 as function of tau such that S1t and S2t plus tau. What is this? This is first signal, this is second signal, and their multiplications. Okay. Along with this multiplication, I have mathematically also defined over here some parameter capital T. What is capital T? Capital T is actually period of measurement. Okay, what is capital T? Capital T is period of measurement, because whenever we are measuring these signals at some instant, if you simply measure at one instant, then you will not be getting something. What you have to do? You have to do the time averaging of that entire signal. So to do time averaging, we have done this integration from minus t by 2 to plus t by 2 over dt, okay, and then 1 by t, because this will be giving you additional t, so this 1 by t. And one important point is limit t approaches to plus infinity. What is the meaning of this?
बहुत ज़्यादा टाइम के लिए इसके एवरेज वेलोसिटी.
Yes, so period of measurement should be such that large, so that the instantaneous fluctuations are actually averaged out. Is this point clear? So instantaneous fluctuations are averaged out. So that is the interest. All are clear with this point? So this R12, now whenever you will be doing the cross correlation, you will be choosing different values of tau. Okay, and you will be getting corresponding to different values of tau, say tau 1, tau 2, you will be getting different values of this R12, say x1, x2, x3, etc. The value of tau at which this x is maximum, that is the actual phase difference between the two signals, corresponding to which your signals are self similar. Is this point is clear? So this is how you can define this function. So this is called as cross correlation function. Is this point clear? So this is nothing but our cross correlation function. So this is the measurement principle is shown over here.
क्रॉस कोरिलेशन फंक्शन हम एवरेज वेलोसिटी निकालने के लिए यूज करते हैं.
No, not average velocity. So this is, we are determining what we are doing. We are considering that this signal is deviating when our, yes, so you can say here average velocity of bubble. Okay, average velocity of bubble. But moreover, Yeah, this time average means whenever you will be doing this S1T measurement, na? So this will be as function of time. So that is for time average quantity.
Multiple peaks in time.
Yes. Okay. So if you see in reality what is happening, in reality it is not giving you the velocity of bubble. It is giving you the velocity of interface. Okay. So what you have, this is one location, here you have some sensor and detector, then this is location 2 where you have sensor and detector, and D is the distance between the two. So when bubble is passing through first location, then you are getting this type of signal, and when bubble is passing through second location, this is the signal. So say tau star is the time gap in between the two. Okay, so now you have calculated this function r12, and when you have multiplied obtained the value of r12 as function of different values of tau, the tau value corresponding to which it has peak, that tau value is nothing but our tau star. So if from cross correlation I have calculated tau star, then I will be able to calculate the velocity.
सर बीच में बबल की शेप ही चेंज होगी.
I will come in the next slide to that point as well. Okay, so in the next slide that is measured. So what are the challenges with this?
फिर वो वाला जो फंक्शन है वो स्ट्रेट हो जाएगा बीच में.
Many things can happen. I will discuss all the potential issues in the next slide. Okay. So now what you can do, you can expect a question in the exam that data is given of S1 as function of time, S2 as function of time, and then you have to determine, say, velocity based on that data. No physical setup is given, nothing is given, simply data is given. Okay. Now there are possibilities of errors in cross correlation velocity measurement. Okay, so first point is what he just now mentioned, that if there is deformation of the interface. So here you can see at location number 1 this slug was that much big, but at location number 2 slug is only this much small, considering that this photo is at T1 and this photo of slug is at some time T2, which is the difference between the two. Okay, so here you can see that deformation of interface has taken place. So now whatever the velocity you will be getting, that will not be velocity of slug, that will be velocity of slug plus velocity of interface deformation. Is this one clear? Yes. So now you will be getting the combined velocity whenever you have deformation over here. So this is one source of error. Second is, if we have presence of gas bubble, gases are more compressible nature, so these can easily expand and collapse depending upon the local conditions of the surrounding. So this is a case. Here you have at location 1 the lesser volume of the bubble, at location number 2 your gas has expanded. So now whenever you will be doing the cross correlation, you will not be getting precise velocity of the bubble, but you will be getting the velocity of bubble and including the velocity of the interface expansion. Okay. Then third point, here what has happened. So say here you are having this as phase 1, this is phase 2. So you are having some wavy structure. So this initially crest has actually contacted the first measurement probe. So it was expected that if you have to measure the velocity of this crest, that same crest should touch this second probe also. But now this, after this point in between this gap, it has actually flattened. So if it has flattened, now it will not touch this second probe. So once it is not touching the second probe, you will not be able to get the value of velocity of this point. Okay. Third important point is change in trajectory. So here if you have turbulent situation, okay, so if you have turbulent situation within the pipe, then what will happen? Your bubble will not follow the same path. It may happen that the moment it was about to approach second point, it has actually deviated from its path. Again, here you will not get the similar signal. Okay, so these are some of the challenges with.
फोर्थ केस में हमें तो फर्क नहीं पड़ना चाहिए कि हम तो लोकलाइज्ड पे एवरेज कर रहे हैं.
No. The point is, it depends upon nature of the probe. If you are using a non-intrusive probe such that optical, yes, which is sending a light signal and a detector, then it will not affect. But if you are using intrusive optical probe can be intrusive as well. Okay, so if you are using a intrusive optical probe, then actually first interface should touch the probe, then only signal will be reflecting and changing at the detector point. Because in case of intrusive probe, source is also coming through the same line, and then output after reflection is also going through the same point after reflection from this interface. Okay, so that's why if you are using intrusive type measurement, then you will not be having actual velocity. And second important point, even if you have non-intrusive measurement, then also you are assuming that when signal is changing, that bubble has only traveled the linear distance. But here what will be happening, it may take some arbitrary path. So you will not be able to measure the precise exact distance what it has traveled between the two probes. Okay. So these are some of the challenges if you use the cross correlation based velocity measurement. Okay. So that's why whenever cross correlation based velocity measurement is to be used, there are certain guidelines. So what are the guidelines? First point is your sampling rate. So this is data sampling rate or signal sampling rate. Typically signal sampling rate should be greater than 2u, where u is velocity, 2u by L, where L is the length scale of the characteristic length scale of the bubble or entity, whatever you want to measure. Okay, so your sampling rate should be greater than this, then only your signal will be of good quality. Otherwise signal will not be able to capture the details sufficiently. Second important point is this d is the distance between the two probes. Okay, so ultimately if you do uncertainty analysis, then change in velocity by actual velocity magnitude, okay, will be equal to this change of velocity can be written in terms of, because we are measuring the distance, change in distance, delta d by d. Okay, so this distance is u delta t by d. So it means that uncertainty in measurement of velocity is inversely proportional to d. Okay, distance. So it means that if your distance is large, uncertainty will be less. But if you keep large distance, then you may have many sources of error. So that's why distance always you have to keep small. So with small distance, your uncertainty in measurement of velocity will be high. Okay. So it means this method of measurement of velocity gives large uncertainty.
तो फिर optimum position कैसे decide करें?
It is specified. So typically, whatever is your characteristic dimension, okay, of the entity whose velocity you want to measure, your optimal distance between the probe should be less than equal to 3 to 5 L. Because if it is more than that, your uncertainty will be less, but then sources of these errors will be actually coming into picture. Okay. So, but this is the old method. Nowadays, people are going with advanced methods, PIV or.
अगर L मेरा एक से बड़ा हो तो
You will not be having a diameter of the bubble in meters.
अगर सेंटीमीटर में भी देखें तो diameter
It will be even small because centimeter sized bubble also will be having actually huge deformation. So typically you have to use this for the situations where deformations are small. So that is what I am teaching.
दोनों की same होगा ना rate.
Yes, I am teaching you the method. So you have to decide which method will be applicable for your application. Okay, majority of the time cross correlation is cannot give you the idea of the total bubble velocity, but it can tell you about upstream interface velocity. So that is something which people majority of time tries to calculate. Okay, so say whatever the first point is there when just signal has changed, so that will be giving you the upstream interface velocity. So other things we are not majority of time we don't consider when we are applying it for the large sized bubbles. Okay, because their deformations will be huge, we will not be able to accurately determine the velocity, because within the bubble also there can be deformations at different locations and changes in the velocities at different locations. Okay. Then comes next method, which is hot wire anemometry. Okay, so in case of hot wire anemometry, what we do, anyone is having any idea?
Temperature change.
Yes, so we will be putting some hot wire, and then depending upon the flow rate, okay, depending upon the flow rate there will be different rate of heat transfer, which will be either changing the resistance. If we have to maintain constant current in the wire, then we have to change the voltage signal, we can measure that change. Or second situation can be, if we want to maintain the constant temperature of the wire, then I have to maintain same resistance. To maintain same resistance, I have to use some feedback circuit. So how to use that, I will show you. Okay. So we measure the velocity of a fluid from heat transfer between a hot wire and the fluid itself. Okay. Wires typically are made of platinum or tungsten with diameters of the order of 5 micrometer and active length of the order of 1 mm. So in case of hot wire anemometry, your wire whatever you are using for measurement, it is having diameter only 5 micrometer, and active temperature zone which is participating in the heat transfer process is 1 mm. Okay, so small. So that's why hot wire anemometry. Why? Because whenever you place the measurement probe in the medium, it should not actually cause any disturbance on the flow structure. And hot wire anemometry is a popular method of velocity measurements, particularly the measurement of fluctuating component of the velocities in turbulent flows. Okay, so in turbulent flows, if you have to measure the fluctuating component of the velocity, then majority of the time we use hot wire anemometry. Okay. Now you may get this idea that when we are going for that much small length of the wire, corresponding to that whatever the flow interaction is taking place, it may not be in the continuum range. So if it is not in the continuum range, then whatever our relations we will be we have, say Newton's law of cooling etc., will not be applicable. But if we calculate the Knudsen number for diameter of wire greater than 5 micrometers, we get the values of Knudsen number less than 0.01. So it means with 5 micrometer continuum level is established, well established. Okay, so we can use the principles whatever we have studied in heat transfer. Wire temperature should not be greater than 200 degrees Celsius, because whenever we use this method, our interest is to decrease the number of unknowns. Okay, if we introduce more number of unknown parameters, there will be errors and uncertainty propagation. Okay, so that's why our interest is that we should have as many as less number of parameters involved in the measurement. So that's why majorly we wanted to operate in forced convection and the conduction mode. Okay, because conduction so by default will be there, and then majorly we want a phenomena should be forced convection dominant. Okay, so that's why temperature is kept low, because if you go at high temperatures, then there can be significant changes in the density of the fluid medium, which may invoke natural convection effects along with the forced convection effects, and there will be increase in uncertainty. And second phenomenon of radiation can also become important. Okay, so if your temperature is less than 200 degrees Celsius, then these can be radiations and free convection effects can be neglected with sufficient accuracy. Okay. So now you can see the basic principle is whatever rate of heat transfer will be from the wire. So if you have say a hot wire, okay, so how much heat is leaving from the surface of this hot wire? Say wire is having temperature TW and outside fluid is at TF temperature. So H, D is diameter of the wire, L is length. So H pi d L into TW minus TF. This is rate of heat transfer from our Newton's law of cooling. Okay. Now if we assume that we are operating, our wire is operating in the steady state mode. So steady state mode means whatever heat you are supplying to wire, same amount of heat wire is actually giving to fluid. Wire is not storing any heat within this. Okay. So in that case, whatever the current into whatever the power. So power is what? I square RW, resistance of the wire. So whatever the power, electrical power we are supplying to our wire, that power will be equal to rate of heat transfer. So under this condition, my wire can be maintained at constant temperature. Is this point clear? So now typically whenever we do calculate this type of heat transfer, we should be able to predict the value of convective heat transfer coefficient H. Okay, and H value can be written in terms of Nusselt number equal to C times Reynolds number alpha Prandtl number beta. Okay, so then alpha, beta and C values we have to calculate. Now for different flow situations, these values will be different. Okay. Moreover, this resistance of the wire will also be sensitive to changes in temperature. So that's why resistance of the wire can be written in terms of reference resistance times reference resistance plus alpha times TW minus TF into reference resistance plus B times TW minus TF into B times square into reference resistance. Okay, so it means that now you have so many unknowns. If you have to calculate H, then you should know C, alpha and beta. And if you have to accurately know the prediction of wire resistance as function of temperature, then you should also know the exponents alpha and beta. Okay, RF will be known, reference resistance. Okay, at some reference temperature. So these many unknowns once again will be resulting in errors. So though fundamental principle is this, but whenever this is implemented in the practical level, what is done? This is the simple relation. Directly input power and resistance are given in terms of simply three unknowns A plus B, U, N. Okay. So here A, B and N. These three you need to calculate. If you do, and of course these three, how we will be calculating? These three we will be calculating from the calibration procedures. Is this one clear? So here what we need to do? We need to do calibration in order to determine the values of these exponents. Now by looking into this left hand side, whenever you will be doing the actual measurement, in your actual measurement two parameters can change. What are the two parameters? Reference resistance will be constant always. So either depending upon value of velocity, either you can have change in current or you can have change in resistance. Okay. So when you have change in resistance will be leading to changes in temperature and ultimately also changes in current. Okay. So there are two things, either you can maintain constant value of current and then see what is the change in resistance or voltage. So that is called as constant current mode of operation. Okay. And second mode of operation can be, you will be maintaining always the same value of resistance. So to maintain same value of resistance, what you have to do? You have to use some feedback circuit, because resistance is sensitive to temperature. Okay, so whenever temperature will change, corresponding to that resistance will try to change, but your feedback circuit will activate and it will switch on or switch off the power to maintain the constant temperature of the wire. So that is called as constant temperature mode, and in case of constant temperature mode you will be regulating the value of the current to maintain the same value of temperature. Okay, is this point clear? So this is the equation which is used at the practical level, and this equation is decided in such a way so that we have lesser number of parameters. Is this one clear? Now typically the coefficients are extremely sensitive to small changes in the wire conditions such as fouling of the wire. Therefore calibration must be extremely careful and it should be frequently verified. So say you have used the anemometer for a month, then again if you are using, then please go for calibration because it is sensitive to many factors. Okay, then two modes we have: constant current mode. So in constant current mode we measure the changes of the electrical resistance, and typically we can simply use a Wheatstone bridge to measure the changes in the resistance. Okay, and second mode is constant temperature mode. So in case of constant temperature mode we should have a feedback loop circuit which will be able to regulate the current in order to keep the wire temperature constant. Okay, so unless or until whenever you see that okay temperature has started falling, it should start increasing the current. Once temperature has reached the value, it should start decreasing the current. So you have to constantly regulate the value of the current. So that's why you should have a feedback circuit over here. Okay, then out of these two modes, if you see, the dynamic response is, so as per your understanding, dynamic response should be faster for which of these cases? Dynamic response means response of the signal with time, or say if your flow structure is turbulent. So in case of turbulent flow structure, what will be happening? There will be random and fast variations, fluctuations in the velocity field. So which out of two can be used for measurement of these fluctuations? So of course constant temperature, but can you tell me why? See, typically in case of constant current mode, what we are doing? We are maintaining the same value of current, and corresponding to same value of current, depending upon the changes in the flow, our resistance is changing. Okay, and in order to change the resistance, its temperature should change. Temperature of the wire should change, then only resistance will be changing. So it means that we should allow sufficient time for the heat transfer to take place. After that only there will be change in resistance, and then that change can be recorded. Okay, so that is something which is called as thermal inertia of the system. Okay, so this is the thermal inertia of the system. So typically the thermal inertia of the system is actually more in comparison to the second mode, where we are simply regulating the current using the electrical circuit. Okay, so if electrical controller based circuit is used, it will be responding fast in comparison to the time taken by heat transfer. So that's why electrical inertia of the system will be less. Now in first case we have of course both inertia, electrical as well as thermal. In second we have only the electrical inertia. So that's why dynamic response is much faster for constant temperature anemometer. Is this point clear? So this is only I have explained. Now whenever you will be using the hot wire anemometer for measurement of a multi-phase flow situation, then you will be expecting signal something like this. Say this is your voltage signal as function of time. So this voltage was having small fluctuations, then there is sudden fall, again small fluctuation, sudden fall. So basically, when you have this sudden fall, this is corresponding to the presence of dispersed phase. Okay, and when you have, because say if you have a gas and liquid, what will happen? Gas, rate of heat transfer will change. Depending upon that, value of signal will change significantly. So once you have significant change in the signal, it means this represents the location of presence of a dispersed phase. And when you have fluctuations at the same average value of the signal, this represents the measurement of velocity in continuous phase, and all these fluctuations are corresponding to turbulent flow situation. Is this point clear? So if you have a constant signal, it means flow is steady. Flow is smooth. But once you have fluctuations in the continuous phase, so this higher value of signal is continuous phase. With higher value, if you have a smooth signal, then it is a smooth continuous flow. And if you have fluctuations, then this is nothing but the turbulent fluctuations in the velocities. Okay, and these fluctuations can be calculated using this signal. So you have to analyze this signal to calculate these fluctuations. But this significant fall will be giving the presence of the dispersed phase. Okay. Now, the measurement of dispersed phase velocity again can have some errors. Why errors? Because when your probe is there, at the probe location, when interface will be approaching, then some micro level phenomenon such as interfacial tension and wettability will come into picture. Okay, so if you have, say, this as your probe wire, so along the probe wire, if say this is gas, this is liquid. So this is gas means it's a big gas bubble. But when you zoom at the, so this, it means you are zooming at this diameter of 5 micrometer. So if you zoom at this level, you will be finding that there is deformation of the bubble interface. Okay, so your gas bubble has deformed something like this. So before this gas bubble completely encloses the probe, it has partial wetting. Okay, so theta is the angle which is occupied by this particular gas, and this theta is nothing but function of, so this over here represents the interface velocity. So this theta is function of interface velocity, delta rho, density difference between the two phases, and sigma, surface tension between the two phases. Okay, and typically this is your voltage signal. This slope of the voltage signal is nothing but equal to d theta by dt. So rate at which your interface will be angularly wrapping the probe, that will be equal to the slope of the voltage signal once it has started changing immediately at this location. Is this point clear? Okay, so if you have to calculate this interface velocity, the rate at which interface is wetting the probe, that you can simply determine by considering k times dV by dt at location A. Is this point clear? All are clear with this idea? So by simply measuring the slope of this point, actually you can measure the velocity of the interface. Okay. So this I am talking about a single bubble. You can have now multiple bubble present in the system. So wherever you have bubble, then at each and every bubble you need to move the probe location. So that is something which is not very feasible, because typically hot wire, this probe will also be costly. Okay, so this type of device is majorly used for localized velocity measurement. If you have to use local velocity measurement at all the points in the domain, then we go for some more advanced methods which are such as particle image velocimetry. Okay, so about particle image velocimetry I will discuss in the next class. One important last point I want to make over here is that because of this interface wetting, this type of device is not very much suitable for the phases in the saturation condition. Okay, so it means if you are using say boiling or condensation, so one phase is vapor and second phase is liquid of the same substance. So in that type of situations, this method is not having good accuracy. It is typically recommended for two component systems. So say if you have air bubble present in the water, or you have some kerosene bubble present in the water. So in two component system, for both liquid as well as for gas liquid, it works well. But if you want to utilize this method particularly for phase change situations where the two phases are nothing but constituting of the same component, molecules of a same component, so there, because of these wetting conditions, you will be finding that accuracy of the system is not that much good. Yes, because there you have multi-component system. Okay, and typically hot wire anemometry is very popular method for measurement of the fluctuations in velocity for turbulent flows. Okay, okay, so we will discuss about particle image velocimetry in the next class.